Greetings, students. This is the second set of notes about geologic time. It's called relative and absolute dating. This image, just take a look at it, shows some different rock layers. And you can use the relative positions of the rock layers to kind of figure out what happened and be able to tell which rock is older than the other rock. So there's two methods of dating rocks, relative and absolute. And we'll start off with relative. Relative dating is saying that one rock is older than the other based on their position. Absolute dating is where you tell the exact age of a rock or close to the exact age of a rock. So relative dating is determining whether a rock, fossil, or other event is younger or older than other objects or events. It shows a relationship. For example, layer A is younger than layer Q, or Andrew is older than his sister. You only know the age relative to another object or item. In order to use relative dating, there are some rules you must follow, like the principle of original horizontality, the law of superposition, disturbances, the law of cross-cutting relationships, and inclusions. The principle of original horizontality states that when it comes to sedimentary rocks, they form in horizontal layers. So remember, sedimentary rocks always form at the bottom of a body of water, one layer on top of the other. They can later be exposed through processes like erosion, faulting, and uplift. When you can see all the layers, that is sometimes called an outcrop. The individual layers are called rock strata. Here we have some folding going on. The layers are no longer horizontal, but they were originally horizontal. And the same with the layers of rock in this picture. They were originally horizontal, but there was some tilting. And then that F layer on top, that's a new horizontal layer that's formed since the tilting happened. A lot of other things happened in this picture too, and we'll get to that. The law of superposition states that the newest rock layers are at the top and the oldest rock layers are at the bottom. The layers that form first have new layers forming on top of them all the time. So eventually, the older layers get pushed down further and the newest layers form on top. This is the case as long as the rock strata have not been disturbed. So, law of superposition means youngest on top, oldest on the bottom. Think of a stack of books. The book you put down first is going to be the oldest, and if you stack books on top of it, the book you put down last is going to be on the top. That's the law of superposition. But there's different disturbances that can occur that can stop that from being true, like folding, tilting, faulting, breaking, igneous intrusions, contact metamorphism, and something called unconformities. And we're going to talk about these one at a time. Folding and tilting. This can happen at a convergent boundary or a reverse fault. When rock layers are pushed together, they often get folded or tilted. Faults are giant cracks in the earth that cut across rock layers. Sometimes an event such as an earthquake can break a piece of rock strata away from an outcrop. So remember from the plate tectonics unit, a fault is a break or a crack in some rock. Here's a real-life picture of some faulting that has occurred. On either side of the fault, the rocks no longer line up, but they used to. Igneous intrusions. This is when a layer of igneous rock forms when magma melts through sedimentary rock layers. A vertical igneous intrusion is called a dike, and a horizontal igneous intrusion is called a sill. The image here has both dikes and sills. Here's pictures of real-life sills and real-life dikes. And these do not form horizontally, they cut through. Disturbances, contact metamorphism. Rocks that get heated to high temperatures without melting become metamorphic rocks. This is often near an igneous intrusion. There will be a small region where metamorphic rocks are created. So you have a pocket of magma. It's called a pluton. And where the rock isn't melted, but it's near the melted rock, there's going to be metamorphic rock. Another disturbance is called an unconformity. And that's when there's a pause in the formation of sedimentary rock. If a lake or an ocean dries up for a period of time, the sedimentary rocks stop forming and they may get weathered and eroded during that time. And then afterwards, the lake or the ocean might come back and start the forming of sedimentary rocks again. So the unconformity in this picture is shown by the black line. So the bottom 3 layers formed at some point in time underneath of some water, and then the sedimentary layers stopped forming, and erosion caused that kind of jagged appearance of the line instead of being perfectly straight. And then later on, there was more sedimentary rock forming on top. This break in time where the new sedimentary rocks were not forming is called an unconformity. It often happens as a jagged layer where the other layers are close to perfectly flat. So different kinds of unconformities are disconformities, nonconformities, paraconformities, or angular unconformities. The law of cross-cutting. This states that when something cuts across rock layers, such as a fault or an intrusion, the cross-cutting layer is newer than whatever it is cutting across. So in this picture, D would be an igneous intrusion. It has to be newer than layers B, A, and C because it's cutting across them. B, A, and C were already there to be cut across. D is not cutting across E, so E is probably newer than D there. F is newer than B, F, C, and E because it's cutting across all of them. So here's an igneous intrusion cutting across some sedimentary layers. That igneous intrusion has to be newer than the sedimentary layers it cuts across. And then there's the law of inclusion, when one layer contains pieces of another layer of rock. In this case, the fragments must be older than the layer that contains them. So in the picture, that rhyolite lava flow contains pieces of the basalt. That means the basalt is older. And the basalt contains pieces of the sandstone. That means the sandstone is older. Let's take a closer look at that. The goal is to figure out the order of rock layer formation, including major events like faulting. It's pretty simple if you just have sedimentary layers, oldest on the bottom, newest on the top. But if there are disturbances, you have to check for one rule at a time. We'll do a little time practicing here. Which layer is the youngest in the diagram? The most recently formed layer. Well, it would have to be D, because D is cutting across all the other layers, including the fault. And you can see D is igneous rock, which forms from molten rock, and then all along the edges of D is the symbol for contact metamorphism as well. But D would be the youngest layer in this diagram. Which layer is older, A or C? Well, using the law of superposition, C is lower than A, and therefore would be older. What types of disturbances can you find in this diagram? Well, I've already talked about some of them. It looks like there's an igneous intrusion, that would be D, and then the diagonal black line looks like a fault, and there's movement along that fault, and the contact metamorphism. which rock formed first in this diagram, the lowest horizontal layer is usually going to be the one that formed first. So B is lower down than C, D, and E. A cuts across it, so A is newer as well. Which letter is the igneous rock? Well, chances are E, D, C, and B are sedimentary because they're horizontal, and then A is igneous rock. It's possible that E, D, C, and B are igneous, but if you're not shown that it's an intrusion, it could be a sill of igneous rock, but we'll just assume that A is the only igneous rock here. Which happened first, C or A? Well, using the law of cross-cutting, A cuts across C, so A must have happened after C. So C happened first. Here's another example. Which event happened most recently? Well, we've got a bunch of sedimentary layers, and then a couple of dikes and a couple of sills. The lava flow at the top is probably going to be the most recent, and you're given the ages of some of them as well. And you're also given the ages of all the igneous rock here, so you can tell which dike is the oldest by just reading the ages. But the diagrams get pretty complex. Which number is the most recent here? You'd want to use the law of cross-cutting to figure that out. Any layer that's cutting across all the other layers is going to be the newest. Yes, there is a fault in this diagram. See if you can find it. And then eventually, once you get practice with this, you will be asked to list the layers and events from newest to oldest. So that's a bit of a challenge. And you could do the same thing with this diagram, but I'm going to move along. We're going to talk about absolute dating now. So relative dating is this thing older than that thing? But you don't know by how much. You don't often know exactly how old. Absolute dating gives you the exact age of a rock in years, and it's close enough to exact. You don't get it to the year, but you probably get it to the millions of years. And we got to go back to physical science to understand this. Just like everything else, rocks and minerals are made up of atoms. Atoms are made up of subatomic particles, protons, neutrons, and electrons. Protons and neutrons are in the nucleus of an atom. Electrons orbit the nucleus. An isotope is a version of an atom that has an unusual number of neutrons. Usually you can count on an atom to have a particular number of neutrons, but some atoms have various versions, and those are called isotopes, when the number of neutrons is different. So here's an example: carbon-12, carbon-13, and carbon-14. 99% of the carbon is carbon-12, but there's also carbon-13 and carbon-14 in nature. Some isotopes of certain atoms are unstable. This means that from the moment they form, they start the process of radioactive decay, and that's when the nucleus of an atom spontaneously breaks down, ejecting matter and energy. There's an artist's depiction of that occurring. This process changes an atom because it loses part of its nucleus, including protons and neutrons. So the number of protons is what defines an atom, so it actually would become a different element. And the atom that it starts at, the unstable one, is called the parent isotope. Radioactive decay occurs, and then you have the daughter isotope, which is stable. The unstable atom prior to decay is called the parent atom, or the parent isotope. After it decays, it stabilizes to become the daughter atom, or daughter isotope. So another way of describing radioactive decay would be to say the process through which the unstable parent atom decays into the more stable daughter atom. Here's some examples of isotopes that decay into daughter atoms. Carbon-14 decays into nitrogen-14. Potassium-40 decays into argon-40. And uranium-238 decays into lead. These are not only examples of unstable isotopes, but they are the most useful ones when it comes to dating rocks. Each parent-daughter combination in the process of radioactive decay has a unique rate or speed at which that decay occurs. The rate at which the decay occurs is most often measured as a half-life. Half-life is defined as the amount of time it takes for 50% of your parent atom to decay into daughter atoms. So when the rock is formed, you have 100% parent atoms. After one half-life, you have 50-50 parent and daughter atoms. After two half-lives, you lose 50% of your parent atoms again. So each time a half-life passes, you lose 50% of the parent atoms. And that can be shown in graphic form. 100% of the atoms are parent atoms at first, and then after one half-life you have 50% parent atoms, and then 25%, and then 12.5% parent atoms, and so on and so forth. So after one half-life, 50% parent atoms and 50% daughter atoms. After two half-lives, you have 25% parent atoms and 75% daughter atoms. So look at it on the chart. One half-life, you have 50-50 red and gray. After two half-lives, only 25% of the atoms are still red. Each time a half-life passes, you lose 50% of the parent atoms, but they become the daughter atoms. And as the parent atoms decrease, there's a proportionate increase in the number of daughter atoms. So when you have 12.5% of the parent atoms remaining, at that point you have 87.5% daughter atoms. So when the rock forms, once again, 100% of the radioactive elements are parent atoms. And then after a half-life, you have 50-50, two half-lives, 25-75. And you can calculate the age of the rock this way by looking at the ratio of parent atoms to daughter atoms. So what is the percentage of daughter atoms after three half-lives? Well, you have, I just actually gave this answer, you have 12.5% parent atoms left after three half-lives. So take 100 and subtract 12.5, you get 87.5. This method of dating using half-life is sometimes referred to as radiometric dating. And you see in this diagram, the same thing is happening. You have half-lives going by, and the number of red or parent atoms is decaying into blue daughter atoms. But in this case, in this example, the half-life is 10 minutes. And for some elements, that would be the case. They wouldn't be very useful for dating rocks, but you do have unstable radioactive elements where the half-life is 10 minutes or 10 seconds even. So in order to find the exact age of a rock, you compare the ratio of parent atoms to daughter atoms, and based on how many of each are present, you use the known half-life of that isotope to calculate the age of the rock. Here's another look at the graph. For example, if they see 25% parent atoms and 75% daughter atoms, it bears to reason that two half-lives have passed. Depending on the unstable isotope that is being used, two half-lives can mean very different ages of the rocks. If it's carbon-14, there's a half-life of 5,700 years. This half-life is relatively short compared to other half-lives that are used for dating rocks. Carbon-14 is most useful for dating things that are 50,000 years old or less. It is often used to date human artifacts. Potassium-40 has a half-life of 1.3 billion years. This method is most useful in dating rocks that are at least 100,000 years old. And uranium-238 has a half-life of 4.5 billion years. This method is most useful for dating rocks that are older than 10 million years old. So that is the notes on relative and absolute dating. This is what your page would look like if you typed it all up on one slide, or you can use my fill-in-the-blank notes or handwrite it. It's up to you, whatever works best.